Welcome to the fascinating world of prime numbers. But what are prime numbers? Prime numbers are the building blocks of mathematics. They are the foundation of many important concepts in number theory, cryptography, and computer science. In this video, we will explore the definition of prime numbers, their history, and their importance in our lives. But what is a prime number? A prime number is a natural number greater than 1. That is not a product of two smaller natural numbers. For example, 5 is a prime number because the only ways of writing it as a product, 1 by 5 or 5 by 1, involve 5 itself. However, 4 is not a prime number because it is a product 2 by 2 in which both numbers are smaller than 4. Prime numbers have been studied for centuries. The first known mention of prime numbers is in the Babylonian clay tablets from around 2000 BC. The ancient Greeks also studied prime numbers, and Euclid, the famous Greek mathematician, proved that there are infinitely many prime numbers. Prime numbers are important in many areas of mathematics and computer science. For example, they are used in cryptography, which is the science of keeping information secret. Prime numbers are also used in error-correcting codes, which are used to ensure that data is transmitted accurately. In this video, we will explore these topics in more detail and learn more about the fascinating world of prime numbers. So, sit back, relax, and enjoy the journey. But wait, there's more. Did you know that prime numbers can be used to create beautiful works of art? The artist Piet Mondrian. Mondrian was inspired by the simplicity and beauty of prime numbers, and he used them to create his own unique style of art. So, as you can see, prime numbers are not just important in mathematics and computer science, they can also be used to create beautiful works of art. Let's dive into the fascinating properties of prime numbers. First up, we have the fundamental theorem of arithmetic. Now, this may sound like a mouthful, but it's actually a pretty cool concept. Essentially, it states that every integer greater than 1 is either a prime number itself, or can be uniquely expressed as a product of prime numbers. For example, take the number 12. It's not a prime number, but we can express it as 2 by 2 by 3, which is a unique product of the prime numbers 2 and 3. Similarly, the number 100 can be written as 2 by 2 by 5 by 5, which is the unique prime factorization of 100. Now, you might be thinking, okay, that's neat. But why is this important? Well, the fundamental theorem of arithmetic is like the foundation of a house. It's the basis for many other concepts and theories in number theory and mathematics as a whole. But let's make this a bit more fun. Imagine you're a detective trying to solve a case, and the clues you have are a bunch of numbers. With the fundamental theorem of arithmetic, you can break down each number into its prime factors, just like a detective breaks down a case into smaller pieces of evidence. And just like a good detective, you can use these prime factors to uncover patterns, relationships, and ultimately, the solution to your case, or in this case, your math problem. Speaking of patterns, did you know that every even number greater than 2 can be expressed as the product of 2 and another number? It's like the number 2 is the ultimate party animal, always showing up to every even numbers party. But don't worry. The odd numbers have their own exclusive club too. They're all products of prime numbers, just like the cool kids in high school. So, the next time you see a number, don't just take it at face value. Break it down into its prime factors and see what secrets it might be hiding. Who knows? You might just uncover the next big mathematical mystery. All right. Let's move on to another fascinating property of prime numbers, the fact that there are infinitely many of them. Now, this might seem counterintuitive at first, After all, prime numbers are special numbers that follow strict rules. So how can there be an endless supply of them? Well, let me tell you a little story to help illustrate this mind-bending concept. Imagine you're at a party, and there's a group of people who claim they can list out all the prime numbers in existence. You're skeptical, but you decide to hear them out. They start listing off prime numbers 2, 3, 5, 7, 11, 13, and so on. But just when you think they're making progress, you decide to play a little prank on them. You take all the prime numbers they've listed so far and multiply them together, then add 1 to the product. For example, if they've listed 2, 3, 5, and 7, you multiply those numbers to get to 110 and then add 1 to get to 111. Now, here's the kicker. The number you've just created, to 111 in this case, is either a prime number itself or has at least one prime factor. That wasn't included in their original list, you see. By constructing this new number, you've essentially proven that their list of prime numbers can never be complete. No matter how many prime numbers they list, there will always be at least one more prime number that they've missed. This clever proof by contradiction shows that the supply of prime numbers is truly infinite. It's like a never-ending game of whack-a-mole, where no matter how many prime numbers you identify, there's always another one popping up somewhere else. But don't worry, this isn't some sort of mathematical torture. It's actually a beautiful illustration of the richness and complexity of the prime number universe. Just when you think you've got them all figured out, they throw you a curveball and remind you that there's always more to discover. So, the next time someone tries to tell you they know all the prime numbers, just smile and remember this little party trick. It's a surefire way to keep the prime number party going forever. Now, let's talk about the distribution of prime numbers and two of the most famous mathematical concepts related to this topic, the prime number theorem and the Riemann hypothesis. First, let's address the elephant in the room. Prime numbers seem to be scattered randomly across the number line like a bunch of unruly teenagers at a school dance. But as it turns out, there's actually a method to their madness. Enter the prime number theorem. This theorem tells us that the number of primes less than or equal to a given number, let's call it x, is approximately equal to x divided by the natural logarithm of x. I know, that sounds like a mouthful, but bear with me. Imagine you're a bouncer at an exclusive prime number nightclub. As the numbers line up outside, you start to notice a pattern. The further down the line you go, the fewer prime numbers there are trying to get in. The prime number theorem is like your trusty clicker, helping you estimate how many primes you'll encounter as the night goes on. But here's where things get really interesting. There's a mysterious figure lurking in the shadows of this prime number party, the Riemann hypothesis. This hypothesis, proposed by the brilliant mathematician Bernhard Riemann, makes a bold claim about the distribution of prime numbers. The Riemann hypothesis suggests that the prime numbers are distributed in a way that's intimately connected to the zeros of the Riemann's theta function, a complex mathematical object that's like the secret VIP room of the prime number nightclub. If the hypothesis is true, it would shed light on some of the deepest mysteries surrounding prime numbers and their distribution. But here's the catch: despite the efforts of countless mathematicians over the years, no one has been able to prove or disprove the Riemann hypothesis. It's like the ultimate unsolved mystery, the mathematical equivalent of Who Shot Jr. Ask your parents. So, what does this all mean for you, the aspiring prime number enthusiast? Well, it means that there's still plenty of room for exploration and discovery in the world of prime numbers. Who knows? Maybe you'll be the one to crack the Riemann hypothesis and go down in mathematical history. In the meantime, just remember, the prime numbers may seem random, But there's always a deeper structure waiting to be uncovered. And with the prime number theorem and the Riemann hypothesis as your trusty guides, you're well on your way to becoming a prime number master. All right, let's talk about another mind-bending property of prime numbers. The gaps between consecutive primes can be arbitrarily large. Now, I know what you're thinking, but wait. Aren't prime numbers supposed to be close together? I mean, they're like the popular kids in the number line, always hanging out in their exclusive little cliques, right? Well, not quite. Imagine you're at a party, and the prime numbers are the guests. At first, it seems like they're all mingling together, with the gaps between them being relatively small. You've got your twin primes like 3 and 5, or 11 and 13 that are practically inseparable. And then you've got your cousin primes like 7 and 11 that are still pretty close. But as the night goes on and the numbers get bigger, the prime numbers start to drift apart. It's like they've had a few too many drinks and suddenly need their personal space. Before you know it, you've got prime numbers that are so far apart, you could fit entire football fields of composite numbers between them now. I know this sounds crazy, but trust me, it's true. In fact, mathematicians have proven that for any positive integer n, there exists a prime gap of at least n. That means if you give me any number, no matter how big, I can find two consecutive prime numbers with at least that many composite numbers squeezed between them. It's like playing a game of how many people can you fit in a phone booth, but with prime numbers and composite numbers. And just like in that game, there's no limit to how many composite numbers you can cram between two primes. But here's the really wild part. We don't even need to go that far down the number line to find these huge gaps. In fact, the first known occurrence of a prime gap of length 1000 happens between the primes 370-61 and 371,393. That's right. There are 1,000 composite numbers just chilling between those two primes, like a big number sandwich. So the next time someone tries to tell you that prime numbers are always close together, just remember the party analogy. Sure, they might start off all cozy and friendly, but give them a little room to breathe, and suddenly you've got prime numbers that are social distancing like pros, and who knows? Maybe one day you'll be the one to discover the next record-breaking prime gap. Just don't forget to invite me to the party when you do. All right, let's dive into the world of famous prime numbers and some of the most tantalizing open problems that have been driving mathematicians crazy for centuries. First up, we have the Mersenne primes. These are prime numbers that can be written in the form to P1, where P is also a prime number. They're like the rock stars of the prime number world, rare, special, and always in the spotlight. Mersenne primes are closely related to perfect numbers, which are numbers that are equal to the sum of their proper divisors excluding the number itself. In fact, if depends 1 is a Mersenne prime, then to P1 asterisk to P to 1 is a perfect number. It's like a mathematical match made in heaven. But here's the kicker. We don't know if there are infinitely many Mersenne primes out there. It's like trying to count the stars in the sky. The more we look, the more we find, but we're never quite sure if we'll ever see them all. This is just one of the many unsolved mysteries in the world of prime numbers. Next, let's talk about twin primes and cousin primes. These are pairs of prime numbers that are so close together, they're practically holding hands. Twin primes differ by 2 like 3 and 5 or 11 and 13, while cousin primes differ by 4 like 3 and 7 or 7 and 11. They're the dynamic duos of the prime number universe. But here's the million-dollar question. Are there infinitely many twin primes? This is known as the Twin Prime Conjecture, and it's been driving mathematicians bonkers for ages. It's like the ultimate game of hide and seek. We keep finding more and more twin primes, but we're never quite sure if we'll ever find them all. And then there's gold box conjecture, which states that every even number greater than 2 can be written as the sum of two primes. It's like the ultimate party trick. Pick any even number. And gold box says there's always a way to split it into two prime numbers. But despite centuries of effort, no one has been able to prove this conjecture once and for all. It's like the mathematical equivalent of trying to find a needle in a haystack, except the haystack is infinitely large, and the needle is invisible. But wait, there's more. We've got other famous open problems related to primes. Like the infinitude of Mersenne primes, are there infinitely many of these rock stars? And the existence of infinitely many Sophie Germain primes P, where the P plus 1 is also prime. Talk about a power couple. These open problems are like the holy grails of prime number theory. They're elusive, they're tantalizing, and they've got mathematicians all over the world scratching their heads in frustration. But that's what makes them so exciting, the thrill of the chase, the promise of discovery, and the knowledge that every step we take brings us closer to unraveling the mysteries of the prime numbers. So the next time someone tries to tell you that math is boring, just throw some twin primes, Mersenne primes, and gold box conjecture their way. Trust me, they'll never look at numbers the same way again. All right, it's time to talk about the real-world applications of prime numbers. You might think that these mathematical oddities are just a bunch of abstract concepts with no practical use, but boy, are you in for a surprise! First up, we have primality testing algorithms. These are like the bouncers of the prime number world. They're responsible for checking whether a given number is prime or not. And just like bouncers, they come in all shapes and sizes, each with their own unique style and efficiency. Some algorithms, like the sieve of Eratosthenes, are like the burly, no-nonsense bouncers who can check a whole bunch of numbers at once. Others, like the Miller-Robin primality test, are like the suave, sophisticated bouncers who can quickly and efficiently determine if a number is prime, with a high degree of accuracy. But primality testing is just the beginning. Once we know a number is prime, we can use prime factorization algorithms to break it down into its prime factors. This is like taking a big, juicy steak and cutting it into bite-sized pieces, except instead of steak, we're dealing with numbers, and instead of a knife, we're using mathematical algorithms. And here's where things get really juicy. Prime factorization is the secret sauce behind modern cryptography. You see, when you want to send a secure message over the internet, you need a way to encode it so that only the intended recipient can read it. This is where the RSA encryption algorithm comes in. It uses large prime numbers to create a lock and key system that's practically unbreakable. It's like sending your message in a top-secret spy briefcase that can only be opened with a special combination of prime numbers. But the fun doesn't stop there. Prime numbers have all sorts of other applications: encoding theory, hashing, and random number generation. They're like the Swiss Army knife of the mathematical world. They might seem simple, but they can be used in all sorts of clever and unexpected ways. For example, encoding theory. Prime numbers are used to create error-correcting codes that can detect and fix mistakes in digital data. It's like having a built-in spell checker for your computer files. And in hashing, prime numbers are used to create unique fingerprints for large datasets, making it easier to search and compare them. And let's not forget about random number generation. You know how sometimes you need to pick a random number for a game or a simulation? Well, It turns out that prime numbers are great for creating sequences of numbers that are truly random and unpredictable. It's like having your own personal set of dice that always roll the perfect number. So the next time someone tries to tell you that prime numbers are just a bunch of useless mathematical trivia, you can hit them with all the ways that primes are used in the real world. From keeping our online communications secure to making sure our computer programs run smoothly, prime numbers are the unsung heroes of the digital age. Who knew that these quirky little numbers could be so powerful? Well, folks, we've come to the end of our wild and wacky journey through the world of prime numbers. We've seen some of the most fascinating properties of these mathematical marvels, from their unique factorization to their mind-bending distribution. We've also explored some of the most tantalizing open problems related to primes, like the Twin Prime Conjecture and Gold Box Conjecture. These unsolved mysteries are like the final boss battles of the prime number video game. They're tough, they're challenging, and they're just waiting for some clever mathematician to come along and beat them once and for all. But beyond just being fascinating in their own right, prime numbers are also incredibly important in both pure mathematics and real-world applications. They're like the secret ingredient that makes so many mathematical theories and practical technologies work. From cryptography to coding theory, from hashing to random number generation, prime numbers are the unsung heroes that keep our digital world running smoothly and securely. And the best part? There's still so much more to discover about these incredible numbers. Every day, mathematicians around the world are pushing the boundaries of what we know about primes, uncovering new patterns, new properties, and new applications. It's like a never-ending treasure hunt, where the treasure is knowledge and the map is made of numbers. So, if you've enjoyed this wild ride through the world of prime numbers, we invite you to keep exploring. Dive deeper into the fascinating properties of primes. Try your hand at some of the famous open problems, and see where your mathematical adventures take you. Who knows, maybe you'll be the one to finally crack the Twin Prime Conjecture or prove Gold Box Conjecture once and for all. But even if you don't become a world-famous mathematician, just remember this: prime numbers are all around us, hiding in plain sight, waiting to be discovered and appreciated. They're in the encryption that keeps our online transactions secure, the error-correcting codes that keep our digital data intact, and the random number generators that power our games and simulations. So the next time you see a prime number, give it a little nod of appreciation. These quirky, fascinating, and incredibly important numbers are the building blocks of our mathematical universe, and they deserve all the love and respect we can give them. Thanks for joining us on this journey through the wild and wonderful world of prime numbers. Until next time, keep exploring, keep discovering, and keep loving those lovely numbers. And that's a wrap on our exciting exploration of prime numbers. We hope you had as much fun learning about these mathematical marvels as we had sharing them with you. We couldn't do this without our amazing viewers. So thank you for joining us on this journey. If you enjoyed the video, please hit that like button and leave a comment below. Let us know what you found most fascinating about prime numbers. If you're not already part of the Beyond the Surface community, now's the perfect time to subscribe and ring that notification bell. You won't want to miss our upcoming adventures in math and science. And don't forget to share this video with your friends and family. Spread the love for prime number as far and wide.